That's wonderful. Thank you so much. Thank you for the invitation. Thanks for the kind words. And it's a pleasure being here. So today I'd like to report about what I have been busy with for the last few years. And we had quite a number of eruptions in Europe. While I did quite a bit of work in Indonesia in previous days, but the last few years, compounded by COVID, caused me to focus a little bit on European things. And we had the Palma eruption, but also the Iceland eruption that is still continuing. And I'd like to summarize some of our work there. Some of this is relevant for Indonesia. Other things may not be so relevant, but you may find it interesting nevertheless. And I think particularly the hazard aspects are very profound. And hopefully I can share some of these impressions and experiences with you today. So I would like to talk about sampling lavas in high resolution. And these two eruptions, La Palma and Iceland, gave us the opportunity to sample very frequently. And this gives us a lot of information. I can say right away, lava erupting in a single eruption is not homogeneous. It changes, and that's fundamental. We can learn different things from these changes. And when I was a student, I thought every eruption is kind of the same, and the lava of a single eruption is identical from the beginning to the end, but it is not so. There's a lot more in detail, and this is where this high-resolution work makes a huge difference. So let's go, and here we, start off as young teenagers reading all sorts of books, and I was quite inspired by Jules Verne, The Journey to the Center of the Earth. And here we have Professor Liedenbrock going into Snæfellsnes volcano, and well, he apparently reached the center of the Earth, and he came out at Stromboli volcano, and this implies that the volcanoes are connected deep inside the Earth. But I assure you, it's not a good idea to climb into volcanoes. So we have to do a better job. And one of the jobs is that we can watch the magma that's erupted as lava. And this gives us actually a message from the inside of the Earth, meaning we don't have to go there. We can indirectly infer things. So magma is therefore one of the most important probes into the Earth interior, because it traveled from the source region in the mantle up to the surface, and therefore we can learn about the source region, but also potentially about the rocks the magma passed on its way. And the erupted lava at the surface can be very diverse, and it is the job of the geologist and the petrologist to understand that language. So this is where we are starting. I'm taking you to these two places today, and here we are. There's the Canary Islands, and there's Iceland, both of them in the northern Atlantic, and we'll start with the Canary Islands. The Canary Islands is an archipelago off Africa, Northwest Africa. Morocco is over here, and here we have 7 large islands, and the islands have an age progression. They go younger towards the west, and we believe this is like the Hawaiian model, that we have a stationary hotspot or plume, and the plate is moving very slowly above it. And this implies that the old islands here, they are deeply eroded, they're very flat because they're so old, and then they go steeper and steeper, and the young islands here, La Palma and El Hierro, are the ones that sit right above the plume. And we can also look at the ocean crust anomalies. Here is the old ocean crust, it's Jurassic ocean crust. Here we have the M25 magnetic anomaly, and this is 156 million years old. And you see the trend of the islands cuts across this. So this is a much younger phenomenon, and it cuts across the old spreading system of the Atlantic Ocean crust. If you want to play games about plate tectonics, you can do that. And here we have the Canary Archipelago, old, young, and here we have the Madeira Archipelago. And there is only few islands here, but they seem to follow a similar trend, and you can reconstruct a rotational pole. It's called an Euler pole, and the two actually fit this rotational pole, making the argument about a plume system over a moving plate rather plausible. But I'd like to actually talk more about the eruption of La Palma. I should note that about half of all the historical eruptions in the Canary Islands happened on La Palma, and in fact in southern La Palma. It's the most volcanically active region in the archipelago, and we had a big eruption there 2021. And here's just a few impressions, and we'll go into details now. And the eruption happened on the southern part of the island. Here we have the Cumbre Vieja Ridge. This is this part here. And all of the historical eruptions happened there. The northern part of the island is extinct. It's the Taburiente volcano. And there was a large landslide here. And this one here. And this happened about 550,000 years ago. And a new volcano grew inside, which is called the Bajanado volcano. And after this, the ridge moved towards the south, and that's where we have the historical eruptions. And here's the 1971 eruption. Here is the 1949 eruption. Here's the 2021 eruption. And what I try to say with that is there is no system in terms of that the eruptions go in a particular order. They jump backwards and forwards. And that's an important realization, because that means we cannot forecast where the next eruption will be, and we were not able to forecast where the 21 eruption would happen. So what we can say for sure is that most likely it will be on the ridge, the next eruption, but where, we will not know. And this is, of course, a problem for hazard mitigation. When we look at the projection here we have the 1712, the 1585, 1585, 1949, and this is the 2021 eruption. And you'll see very quickly that these eruptions here were coming from very steep slopes up on the hill, and they form very narrow channels. The problem in 2021 was that here we had a flat area with a lot of people living there, and the eruption unfortunately affected that area. The impressions here in the top right, that's a photo from 1949, and these two in the lower part are from 1971, but the eruption styles are pretty much identical. They haven't changed over the historical time, so they're all fissure eruptions that form lava flows and make sinter cones. So that's good news, because it means we can actually be pretty confident about the style of eruption, but we cannot be so confident about the next place of an eruption. So here's a detailed map, and we don't have to go into all the kind of detailed numbers up there, but the eruption of Tajo Gaita, as it's called, the 2021 eruption, was a little longer than the others, and as you see here, it looks a little bigger, but it's actually just because the ground is very flat and it's spread out. So otherwise, it's a typical rift zone eruption in the sense of the other eruptions on the island of La Palma. So here is a little summary. Scientists knew that there was magma. It's been heralded by seismic activity already in 2017. And the local people may not have been so aware, but the scientists knew something was happening. And in mid-September 21, the seismic swarms intensified, and eventually an eruption began on September 19th in the midday. And the eruption had several active vents, and it emitted about 0.3 cubic kilometers. To give you a reference, Mount St. Helens in 1980 was 0.9. So it's a relatively small eruption. But the VEI, the Volcanic Explosivity Index, was 3, and the plume height was actually several kilometers. The eruption was declared over Christmas 21 after a short period of inactivity. And here is from a clipping from a Spanish newspaper, Dia 1, Day 1, and Dia 87 after 87 days. This is the same house, and you see there's a big sinter cone that had grown. And you can calculate it has grown with a very rapid rate of 3 meters a day. So a very rapid growth, but now it's a monogenetic eruption. So we don't believe that there will be more eruptions on this particular vent. So here's the eruption in full swing. And well, this is the old Takanda Road, and it was blocked obviously by the volcano. That was a big problem for the traffic on the island because you had to go around the island then, but now they have a new road, and you can see the activity from the main craters here on the sinter cone. There's one here, but there's another one up there, and there's yet another one behind. So this is a little video, and I hope I get this to work. This is to give you an impression of the eruption. How do I go there? Yeah, there. Perfect. It's a little loud. So here's several vents erupting. We can play it again. It's so cool. So it's one fissure system, and there are several vents along the fissure, but as so often, one of the vents becomes dominant, and the others die out. At the beginning, and I'll show this for Iceland later, we may have eruption all along the fissure, but then usually one or maximum two of the vents, they become dominant, and they become the main eruption. So, and of course, the eruption produced a lot of pyroclastic material, and this was the house closest to the volcano. And as you can see, this picture up there in the top left, this is from October, late October 21, and this picture is from December. And not only was the house buried, there was also a vent opening up on December 5th, just in front of the house. And I saw an interview with the house owner recently, and she was very frustrated because the house is, of course, broken. But the mayor of the village suggested she makes a volcano museum out of it. And she was so angry. So she just refuses that anybody is allowed on her property. So I don't know what's going to happen to the house, but it's a very spectacular sight where you had the house covered, cracking under the weight. You see the cracks there, and a vent in front of it. So a very dangerous situation. The house is, of course, lost. I don't think anyone can ever live there again. So when we approach the vents, then it looks like this. So a very volcanic, well, desolate landscape. You see the bomb impacts, and of course there's blue haze in the crater. That means sulfur is emitted, and you see also the sulfurous deposits. So this is when you go a little closer, and I could go up to here, and then my stomach didn't play along anymore. I didn't want to go any further, so because it looks a little dangerous, but this is as close as my sampling went. And I'd like to talk a little more about the lavas now, because they were really destructive. And high on the slope, we had these rivers of lava. They were running quite fast, actually. And further down, the rivers were spreading out into fans. So here we have a picture of a river of lava coming down, and out here, it's spreading to make a fan. And this is the problem with the population density here. There's a lot of people living in the area, and the rivers of lava, when they hit the flat ground, they spread out, and it affected a large area. So here's another impression. There's an older volcano cone. It's called Montaña Todoque, and this was before the eruption on the right-hand top side, and this is after the eruption. So the entire area is now completely covered. So this is a picture from October. This is on one of the other old sinter cones. This is Montaña La Laguna. And Todoque, the mountain, is over here. We've just looked at that one. So this is the twin brother, if you will. And this is from October, as I said, and now this is from December. So you see the difference. And the entire area was covered. Many houses, many plantations, but also some islands were left, some areas in between lava flows, and these areas are pretty intact. The problem is only you can't go there because you can't walk over fresh lava. So these were isolated areas, and now they're trying to build new roads to connect these areas again. This is an impression from the village of La Laguna, and this is lava coming into the village. And when I first went there, I sent this picture home to my wife. And my wife was not commenting on the lava. She said, "Oh, the poor tree." So, and she asked me, "Has the tree survived?" And I said, "I'll check on the tree next time." So when I was back a month later, I went back and I checked on the tree, and the tree did not survive. So it was a little too warm for the tree, I'm afraid. So, but you get the idea. There's a lot of damage now, and this has now been cleared out. And this is where the new road starts that goes over the lava field. So here we have an impression of lava in a banana plantation, and the pyroclastic material and lavas covered together about 1,000 hectares of farmland. This is a large area, certainly for Canary Island standards. So here is damage now to the villages, and this is another little video. Let's see that I get. Can you take care of this? So have a look at this. Thank you. And just when the video stops, there was a big explosion because there was a gas tank in the house as well, but I didn't film that because I was running away. So, but you see the damage. This is the blocky AA lava that's a bit further away from the vent, and the problem with that lava is you cannot really stop it. There was a church in the village of Todoke, and the local people were trying to stop the lava, and they were digging trenches. They were thinking in terms of pahoihoi lava, because that would flow like water, if you will. But AA lava moves very differently. It's more like a caterpillar. It rolls over things. And while the local people have admirably tried to save the church, the scientists already said when they started, it's useless. It's the wrong type of lava. And indeed, the church was rolled over by the lava and is now buried under it. So the eruption lasted for 85 days, which is in itself an economic problem. Almost 8,000 people were evacuated, 2,800 buildings were destroyed, of which 1,300 were homes. Over 1,000 hectares of plantation land was covered or destroyed. 70 kilometers of vital roads were cut off, causing a real problem because you couldn't go from north to south on the west side of the island. You had to drive around, which caused a lot of traffic issues. And although nobody died directly in the eruption, there was one accident, but that was because somebody snuck into the exclusion zone secretly, and that should not be the case. But no direct loss of life, but the total estimate of financial loss is 1 billion euro, i.e. 1,000 million euro. So it's very expensive. So here's just a few impressions of the various devastation, and this happened very late. December 5th of the year. Here we have the December 5th lava going over the cemetery in Las Manchas. And this was psychologically very damaging because people thought that the volcano had now even surpassed God and that nobody can stop the volcano. Many people even believe that the devil lives inside the volcano. I can see that, you know, it gets very heated when you're in that situation. Of course, as a geologist, we believe that volcanoes are natural phenomena and that we need to understand them rather than personify them. But there was a lot of psychological problems in the aftermath. The local population was suffering, not only physically, but also mentally. So here's one of those situations where we have lava, and here's a burned car. And I like this picture so much because in my lectures I usually say, pahoihoi lava can make AA lava when it flows and cools. But we cannot make AA lava, we cannot make pahoihoi lava from AA lava because you need to reheat it. And this is the exception because just here, around the car, we have pahoihoi lava and the rest is AA lava. And the burning car was so hot that it reheated the lava. And therefore, I now stand corrected. You can make pahoihoi lava from AA lava, but you need a lot of heat for that. So here we have a burned car, and I think it's a spectacular example of how you can reheat lava. So let's talk a little bit more about the lava field. We have the lava field was expanding. The red area here was the initial lava from September 20th. That's the second day of the eruption. And then the lava field grew. And this pink arm here is one of the last lava flows from December 5th. This is the one that hit the cemetery. And this was, of course, considered very, very damaging. This is Montaña Todoque, I showed it earlier, and this is Montaña La Laguna. This is La Laguna village, and Todoque village is largely buried. So this is the evolution, and we went out there sampling quite consistently. We had a larger team, so I was not there the entire eruption. I was there several one-week spells. And this allowed us to sample lava over the course of the entire eruption. So this is us sampling lava. And on this occasion, we had a camera person from the BBC with us. But, well, we went out there kind of regularly. Whenever the lava came out, within a day or two, we tried to sample it. So this is the thickness map of the lava field. And the vent is, of course, very thick. But here in the central part of the lava field, we're reaching thicknesses of 70 meters. And that will mean that the lava will take years to cool. It's going to take a long time. The lava is thinner down here, and that's where the new road goes across. There, the heat is not so difficult, but you're not allowed to stop on that road, so, because the tarmac is warm, of course, from the heat from the lava. So the maximum eruption temperature was 1140 measured, and then we had 45 million cubic meters of pyroclastic material, and we had 188 million cubic meters of lava. And as I said, 70 meters is kind of one of the thick deposits there, and it goes even over 70 meters. Measured velocities is about 30 kilometers per hour, so it's pretty fast. And it was associated with earthquakes up to magnitude 5. So a little bit of geochemistry here. This is the sample suite we collected. We published this in 22 here in this paper by James Day and many of us. And here we see that there is a difference during the eruption. The first 10 days of the eruption here in blue had a very different composition than the rest of the eruption. And the change was quite rapid. And if you use the task diagram, then the first few days had a tephrite, and then later we had a basanite. This is also exemplified in the thin sections. So here is early lava from the 21st of September, and the crystals are very small. We even have strange minerals in there like reddish amphibole, while later in the eruptions, the crystals are pretty big and they're nice and euhedral. So our suspicion was that we had an early material coming from a more evolved magma reservoir, and then later we had some magma probably from a deeper source. Well, we have to test this, and if it's true, if this is from a shallower reservoir, more evolved, then it should have different isotope signals. We did some rhenium osmium isotopes, and indeed, early in the system, we have a more radiogenic signal, and that is usually only possible if your magmas interacted with some crustal rocks. Then these values become more radiogenic. So we had a good hint that indeed this magma may have come from higher up in the plumbing system, and this is from deeper down, maybe the mantle. And if we look at the seismics, this looks very convincing because we have two major seismic clusters. One is here in the crust mantle boundary area, and one is in the mantle. There's a bit of a discussion where exactly this reservoir sits. There's two groups. One group says it's between 30 and 40. Another group says it's between 20 and 30. For our purpose, that's not the key issue today, because either way, this would be in the mantle, this lower reservoir, and this is actually in the mantle crust transition. So this is the seismics against time, and this is when the eruption started. You can see that here when the magma was rising up. And initially, for the first 10 days, there was no deep earthquakes. They were all shallow. And that's very important, because we said there was a difference in the chemistry. We had tephrite erupting right from the start, and later we had basanite. And indeed, we have this gap here. And that allows us to make this change in the magma composition. So initially, most likely, we had this shallower magma erupting, and then later we had deeper magma coming in. So very interesting, because it's not just one magma soup, it's actually different pockets of magma that have been involved. So we did test this with fluid inclusions, and the fluid inclusions did confirm the deep storage, so we know that this works. And the fluid inclusions did not resolve the shallow system all that well, so we had to use a few other things. And this is where I started to think about, if it's true that the shallow system has interacted with crust, it should sit in the old Jurassic Ocean crust I mentioned right at the beginning. And could we actually use this? Could we see the oxygen crust signal with geochemistry? So, and here is the unpublished data. I'm working on this right now. Here we have oxygen isotopes. This is what I showed earlier, the rhenium osmium, and here the oxygen isotopes. And indeed, the first 10 days give us a lot of spread, a large geochemical spread for oxygen isotopes, and then later it starts to become more flat. So, how can we explain this spread? Well, I had to go back all the way to my PhD, and here's the work we did, 20 odd years ago. Hanstein and Troll, we looked at rocks under the Canary Islands at the ocean crust, and what we found is that the gabbros of the ocean crust, they have low oxygen isotope values because of the heat circulation, while the upper ocean crust has higher values. And therefore, the only real thing that we can use to make these values go down is actually the hot part of the ocean crust. And we therefore have a pretty good indication that the magma reservoir must have sat about here, because we have some lower values and a little bit of higher values. And this gives us a stratigraphic position for the magma chamber. So this is also consistent with the position here, because here we're sitting directly on the old Jurassic Ocean crust between 156 and 100, whatever that is, 150 million years. So we know that the old ocean crust is thick, and it would have this stratigraphy. And in addition to that, the early lavas, I told you, have these weird minerals like reddish amphiboles. In addition to that, we also find a lot of little gabbro xenolith. Here's an SEM image, a scanning electron microscope image of one of those gabbro xenolith. And this gives us a good idea that the deep magma comes from the mantle, but the initial magma was sitting in the crust beneath the island, likely somewhere in the transition between the gabbros and the basalts, and maybe even the sediments. And therefore, the oxygen isotopes confirm the seismics, and that complements the information, so we're getting a really good idea. If you are a geochemist, you want to know the mantle signal for the oxygen, and my advice is don't look at the first 2 weeks of eruptions, because they are often very compromised by these phenomena. But later in the eruption, it's very stable, and if you only look at that stable part, then my best estimate is that the mantle underneath La Palma has an oxygen isotope value of 5.3, and that's very useful if you want to do geochemical modeling. So this is the summary for La Palma, and just a very quick note, we're still working on some of this. From a hazard point of view, we are wondering how these two reservoirs, when they interact, would actually change the eruption patterns at the surface. And there's one problem here, and that is up here we have the earthquake intensity, the number of events, and you see that there was a large number of events, low, large, low, large, low, large, low, and this is a bit of an issue because the local people, they were feeling that the eruption might end very soon when there was less earthquakes, and they were hopeful. But then it started again, and it got weaker, and it started again. And here's a numerical model that we are working with. Here we have two reservoirs, and we're sending magma from one reservoir to the other. And then, of course, once the magma hits this shallow reservoir, you get pressure pulses. And we think that this is the reason for the intensity changes. The bad news is that if you have less earthquakes during an eruption with two reservoirs, you will likely have these changes. And this is not an indication that the eruption will stop. Here is also a little diagram looking at the shallow earthquakes and the deep earthquakes. And I had one of our geophysics colleagues to look at this. We are pretty confident that we can translate these events. So these two reservoirs were connected. It takes a few days from this to translate upwards. But here we're pretty confident that these two reservoirs were communicating by sending magma upwards. But each time a new pulse of magma arrives, it causes problems. Imagine you have a garden hose with some larger reservoirs in between. You can imagine that there is all sorts of complications, fluid dynamic complications, and therefore with this type of double reservoir eruption, we expect large fluctuations. It's not going to be linear, is my point here. So I'd like to talk a little bit more about Iceland now. That was the La Palma story. That's the perfect moment for having a sip of coffee. So, we're going to Iceland now, to Fagradalsfjall first. And Fagradalsfjall, you've seen the images, spectacular eruption. And a word about Iceland. Iceland is, of course, built by volcanoes. It's active for the last 14 million years. The oldest rocks are on the blue ends, and the active zone is where the red material on the map is. And the Reykjanes volcanic belt is just about here. The Atlantic spreads with about 2 centimeters per year. It's very slow spreading compared to the Pacific. Pacific spreads with about 7 centimeters a year. But we also have a plume under the island of Iceland, because otherwise it wouldn't be above sea level. And here is a projection of the plume. And the plume sits probably on central Iceland, but it spreads likely in a mushroom fashion. And therefore, we think there's a plume influence all around the island, including the Reykjanes Peninsula. So the Reykjanes Peninsula continues into the ocean, into the mid-Atlantic spreading ridge. And it's actually not a simple spreading system. It's an oblique shear system. And you can see that here, all the volcanic areas, they're spread out. So we have this type of movement. And in this kind of situation, we open fissures, and the fissures will allow magma to rise up. It's likely more of a passive situation, where we open cracks and magma oozes out, rather than magma forcing its way through. So the eruption history of the Reykjanes can be divided into eruption periods and periods of seismic and volcanic inactivity. So here we have an eruption period, number 3. This goes back 1,000 years before our time calculation, and it was followed by about 1,000 years of inactivity. Here we had a few hundred years of activity again, and followed by a larger, about 1,000-year period of inactivity. Then again, another eruption period of a few hundred years, and then we had up to 900-something years of inactivity. And now Fagradalsfjall started, and Svartsengi started as well. So we are likely at the beginning of a new era of volcanic activity, and we're expecting more eruptions for many years to come. So this is, of course, a bit disconcerting, because it means we have to get ready for a larger volcanic cycle there. So if the past is the key to the future, then we are in for more eruptions. And the predictions right now is that we will have another eruption in Iceland, probably in the next 4 weeks. So it's building up right now, and we're expecting the next one. And the biggest worry that we currently have is, could there be multiple eruptions along the peninsula? And is there a big magma system under the entire peninsula or not? But I'll come back to this a little later. So let's summarize the eruption activity. In March 21, we had the Geldingadalen Valley opening up in the early evening, and a 700-meter long fissure started to erupt. This fissure erupted until April, and then several new craters formed, and then once they started to outpour lava, they started to also decrease, and eventually one of the vents became the dominant vent. So here is a little map. Here's the vent alignment, first vent, second vent, fourth, three, and again you see they're jumping. This is the problem with fissure eruptions. They're not progressive, they're jumpy. There's statistically no reason why they should form an alignment. So the problem with fissure eruptions is they go backwards and forwards. There's a random element, unfortunately. So this is the fissure early on, and here you see vent 1 in the foreground, vent 2 in the background, and then vent 3, etc. And note this little vent here, vent number 5. And let me show you vent number 5 at the end of the eruption. Vent number 5 has become the biggest of the vents. And this is a good analogy. I always say to my students, you may not be the brightest or most successful person at the beginning of your career, but you can catch up. So vent number 5 is a good example for this. Vent number 5 is also the one who had the biggest topographic changes here. Here's the elevation, as you would expect from this kind of system. So this is vent number 5, and here we have a beautiful lava lake, and the lava lake was building up and erupting, and then it was subsiding and building up, and in summer of 21, this was almost cyclic. It was beautiful to watch, and the eruption was in a remote area. Many tourists came there to watch the eruption. There was no settlement in the area, and it was really what some people call a Disneyland eruption. You could go there and enjoy. So here we have a drone view into the lava lake of vent 5, and a spectacular lava crust, and there's just new lava pushing up. And eventually the lava was so much that it spread from this valley here, Geldingadalen, into Meradalen, and also into this valley, Nathagi. And here was a big worry, because if that would continue, it would cut off the road. So people were really worried. They started to make barriers here, and funnily enough, the lava just stopped in front of the barrier. Everybody was disappointed, but it was a really good exercise, because, as we'll show for 2024, the lava barrier concept became really important. It was a very good practice exercise, because now the lava barriers are saving the village and the power plant. I'll come to this in a minute. So here we have the lava arriving in the Nathagi Valley, and the Nathagi Valley is very sheltered. Nathagi actually means the night pastures. That's where you bring your sheep for the night, because it's so safe. But once the lava arrived in the valley, I think it wasn't a good place for sheep anymore. And here's a little sequence. Could you get me the video going of the Nathagi Valley? So now you see it inflating. There's actually lava flowing under the crust, not on top of it anymore. And degassing helps as well. And there you see the lava coming out from inside. And of course it's Iceland, so it's raining. So this was the filling of Nathagi, and it's quite spectacular. As you saw, there was a lot of tourists there as well. So the authorities did not lock the area off. And we had a little bit of wildfires. Here you see burned areas of moss, but overall it wasn't too bad. So, oops, let's go here. But once the eruption stopped in 21, everything seemed fine and over. But just about a year later, in August, the next valley was affected. This is early. This is August 2nd, and here we have a fissure again, and there's eruption along the fissure. Here's some vents, and the fissure was cracking into the mountain. But eventually, this area became the dominant vent, and it looked like this. And this is the fissure end, and there at the fissure end, we have the initial baby volcano that never grew big, and the big volcano is actually here on the other side. So this is the little baby volcano that did not get covered, and you can still go there. Now it's covered in sulfur, unfortunately, but this was a little spatter volcano on the fissure that didn't grow big. And the final eruption was actually along the main sinter cone, and of course this is us trying to sample here and enjoying ourselves. The equipment was a little improvised at the beginning, but we got better as we go along. So, and we had these wonderful situations here. This is actually the 21 lava, and when you see where the new lava was coming, you realize, oh, this lava will be buried very soon. So you go there quickly and take another sample before the new lava arrives, and then you take a break, and then a little later the new lava comes. And then you take a sample from the new lava. So you get 2 years sampled with one trip. So it's quite effective. And this is how it looks then when the new lava covers the old lava. So, and of course, as I said, we were sampling away. This was very efficient when we had situations like this. Here we have the 22 lava reaching on new ground. There was a few places where it didn't cover it. And here, spectacular how it brings in boulders from the subsurface. So here we have a lithic clast picked up by the lava, and this is the furthest extent of the 22 lavas. This is actually right here at this place. So a year later, another eruption ensued, and that was that Litli Rutur eruption. So this was Geldingadalje 21, this was Meradalje 22, and Litli Rutur was up here. You see, it's all aligned in this way. This was the vent, and the lava was flowing down here, and eventually the lava was starting to cover all the lavas from 22 and 21, but for most part, the 23 lava is actually on pristine ground, i.e. it's not covering all the lava. So this is the Litli Rutur cone, and this was early in the eruption, and this was later in the eruption. You see where we had open ground, suddenly we had these lava ponds here and lava flows, and the entire area is now covered with the lava field. So here is another video, and this is how it looks from the surface. You see these sporadic fire fountains, these bursts, but you have very little idea how it looks in reality, and the drones reveal it. It's actually a boiling vent, so there's a boiling lava lake inside. It looks, you know, reasonably peaceful from here, just a poof, but actually it's really violent inside the vent. So, and a few more shots. Here we have the 23 lava going over 21 lava. It's reasonably slow, so you can watch it, you can walk away, it's not too dangerous. And here we have younger lava spreading on fresh surfaces. And there's a major wall of lava. This was coming in 23 on the 21 lava. Here we have a beautiful situation. This is 21 lava, this is 23 lava, and this is 22 lava. And this lava was migrating towards this. And here's a larger image. So here it went a little further. And eventually this lava was actually going over that lava. And that meant there was one place here where we had 21, 22, 23 in the right order, but only one place. And this makes you think, when we look at lava stacks, old lava stacks, how many of those are actually mixed up and how many are in proper stratigraphic order? Something to think about. If you look at stratigraphy and lava stratigraphy and things are changing and jumping, maybe you actually had different lobes coming in at different times. So what looks like flat horizons in lava mountains may actually be a lot more complicated. But here is the three of us standing proud at the place where all the three lavas are above each other. And so this is only one place, exactly this place here. And well, we look like as if we shot a lion. We're very proud to be there, but of course we didn't. So here are a few more impressions of lava sampling. As I said, initially it was a bit improvised, and we sampled a lot of rock. Eventually we got a donation of safety suits from a steel company, and this was a real game changer. Not for the sampling, but suddenly we got a lot of media interest. We got 90 million views on YouTube by now, just because of the suits. The sampling was the same. So, but it looks really cool, doesn't it? So everybody loved it on YouTube, and you feel like an astronaut. So, but of course, all the suits do is they reflect the heat, so you can stay at the lava a little longer. And if there's a blip of magma or so, or lava, it doesn't burn you. So it's actually quite useful, but it's a lot of trouble to put it on. But you know what you do for likes. So, now a bit of geochemistry. There's a lot of plots here, so I'll run you through them. Similar to La Palma, we see an initial change here, and then it flattens out. And this is true for many of the parameters, trace elements, major elements, and this is very intriguing. So again, we were thinking about what's going on. We concluded that there must have been different sources early in the eruption, the first 20 days, and then a different source later in the eruption. The early lavas were more depleted, and the later lavas were more enriched. So if you look at this diagram here, this goes back to Fitten et al. The blue lavas are from early in the eruption, and the yellow ones from later. And we're moving more towards the OIB field. We're getting more chemically enriched. So there is indeed a change here. And this is, of course, true for the other parameters here as well. Here's niobium, zirconium, for example. And here we see this change. So we have a higher resolution here. And initially, people were interpreting this as different mantle reservoirs being tapped. There's different mantle end members, and you can calculate mixtures between them. And initially, it seemed that we had mantle end members more down here, and later more up here. The yellow ones are the later lavas. But I'll give you a little bit of a caveat later, because these workers, Halderson et al., they noted early on that the eruptions tend away from everything that's been measured on the Reykjans before. So something is very strange. And they argued it's a mantle problem, but we are a bit skeptical about that. We're actually thinking this may be also, like in La Palma, a crustal problem. But let's look at this a little further. We went to do oxygen isotopes to see whether we can resolve this. And here we are. So this is the oxygen isotopes. We have low oxygen isotopes in central Iceland, but here at the Reykjanes Peninsula, we have very normal oxygen isotopes, very similar to the Reykjanes Ridge and to the Atlantic Morb. In fact, it's completely flat. There's maybe a little bit of variation early on, but the oxygens did not really resolve anything. We published this paper in June 22 saying that the oxygen is not variable, and if it's really different mantle end members, they're certainly not different in oxygen. As soon as we published this, a few weeks later, the eruptions came again at Meradalia, and of course most people then asked me, so what happened to the oxygen afterwards? And the answer is, it's still flat. This is unpublished data, this is published data, so we're writing this up right now, and here it's still pretty flat, so no real change. So this test failed, but it gave us some other indication. So what else can we do to test this? Well, we did some barometry, and this is from clinopyroxene. And first of all, there's very little water in these magmas, but the barometry suggests about 5 to 2 kilobars of crystallization depth, and that is not in the mantle. The mantle starts down here in Iceland, in this part of Iceland, So we are in the crust, lower to mid-crust. And that's very intriguing. If you want magma to come from the mantle, you would expect the crystals to have grown in the mantle. But that's not quite what it is. So initially our model was that we may have had a reservoir in the upper part of the lower crust, maybe a little bit above the mantle, and some pockets early on to explain the eruptions of the first 2 weeks or 2-3 weeks. But it's also not quite true, because eventually we did osmium isotopes, and the first 2 weeks are going crazy again in osmium. Not in oxygen, but in osmium. And again, these values indicate that we must have some radiogenic crust involved. So these are in fact the highest osmium isotope ratios of any recent eruptions in Iceland. So this is quite a severe observation, and it requires us to have magma sitting in the crust up there. So this model is not bad, but it's also not perfect. And a little later, after the eruptions at Fagradalsfjall stopped in 21, a new eruption series started in this place here called Svartsengi, along a fracture system that's referred to as Sundnukur, and this is this area here. So Fagradalsfjall is over here, and suddenly in late 23, a new eruption cycle started here at Svartsengi, and here we have some bulging of the crust. While this was remote, this area is populated. So there is a power plant here, there is a village here, there's a major road here, and the Blue Lagoon, the major tourist attraction in Iceland, is also there. Suddenly, the eruptions got very serious. What was a tourist Disney eruption suddenly was actually a real problem. And in early 24, we had a crack opening up, sending lava into the town of Grindavik. And what was happening then is that the Icelanders, they built lava barriers, lava dams around Grindavik and around the power plant. And here you see the lava coming, flowing along the barrier, and they're just closing the last gaps before the lava arrives. And this is what they're doing right now. They're building more lava dams because there's a new eruption likely to happen in the next 2 to 4 weeks. So here's the timeline, and initially we had these 3 eruptions, and they were quite spaced out, and they were in a remote area. But now we have bang, 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 a quick series of eruptions. Actually, I haven't even added all of them because it was so quick, and we're expecting another one. And not only is it faster, the volumes are bigger as well. So we have more. It's faster and bigger. And this is what we anticipate to go on likely for quite some time. So, and by now it's reached the outer parts of the Blue Lagoon. This is the parking area of the Blue Lagoon, and this is the lava barrier. The Blue Lagoon and the power plant are behind the barrier. But, well, let's see if they can raise the barriers faster than the lava arriving. So, this is the lava field from Fagradalsfjall. This is the Sundnukur lava field, and by now it's actually gone around Grindavik. This is not the latest map. Here's the latest map, and here you see the lava has gone down, and these red ones are the barriers, the lava barriers. And the lava barrier has basically saved the town on several occasions, here and here. So it's surprisingly effective. There's a bit of a worry that when the lava reaches this pond here, we might get some phreatic explosions. But let's see about that. So far, the lava has not reached the coast yet. Here's a few impressions. There's a whole cohort of trucks and diggers ready to build the lava. The roads are left open when the lava comes. They close these kind of barriers very quickly to allow traffic before the lava arrives. So this is the Blue Lagoon, and Grindavik is just behind that hill here. And this is the spa area with the power plant of Svartsengi, and the power plant supplies electricity and warm water to the main international airport at Keflavik. So if this power plant was to stop, we would have a serious problem. So, and as I showed before, this is the lava arriving at the Blue Lagoon, and the first buildings are burning. So here we have some impressions from the lava that went into the town of Grindavik, and it stopped there just about at this fence, very peculiar situation. The wooden fence was not burned because this lava was already cold. So here we have one of these houses that got affected by the tectonics. The house here is bent, as you can see. It's a tilted house. And there's a little video here. Let's see if we can get this to work. Hello, hello, I'm here in Grindavik, and I'm just looking at the various damages. We have it July now, 24. This is from earlier this year, and here you see the road has been filled in. The crack that went through the road has been filled in, and there is a metal bridge over it now, but the cracks continue, of course, beyond the road. These are cracks that come due to dike intrusion, but also due to tectonic movement, and there's a building here, and of course the building is affected as well. So here you are, a big crack in the building, and over there is another one. There's a few smaller secondary cracks here as well. Let me get a little closer so you can just about see them here. I think there's two parallel cracks here, and they meet up with the main crack over there. And of course these things are barely fixable. This building has probably permanent damage. Hopefully some of these things can be salvaged nevertheless. Okay, thank you very much and all the best. Hello. So this is another video. This is the hottest road I ever driven on. Yeah, can you do that? So this is the new lava road, and you must never stop on this. Volcano, or is it two volcanoes? So these are very important questions, and I put up these three hypotheses here. And that is that hypothesis one, we have a reservoir in the Bandung that feeds all of these things. This was the initial outer down here, and then the idea that Bindemanadal and our things came up with this. Maybe we have different pockets to explain the different type of material, but we also have influx from the mantle, but this would be a more complicated plumbing system that's partly branching and wouldn't require the same amount of magma, would be less severe than this. And judging from previous work in the area, some people postulated there could be a large system under the entire Radiant Peninsula that could supply several of those older systems. If this is true, then we actually have magma under the capital of Radiant. And that would be very disconcerting. So you don't want to have magma under your capital. So this was important to find out. So the first thing we did is we tested whether the chemistry of the lava could change. And here we have the variation, major elements, trace elements, and we have this initial change. I showed you before. In red is now the first spark in magma, and they seem to be of the same thing. Good news. It seems to be one volcano, not two. So big relief. And when you look at the minerals, this is laser ablation data on olivines. There's different types of olivines. So this is the butternut kettle olivines. And here we have the sparkling things, the finger, and here they even overlap. The pink ones are the ground cross, the red ones are the bigger crystals, and here there seems to be a continuation. So the minerals would also imply that we are talking about the same matter. So, great news. But then we need to also ask, if you have a problem somewhere, You are going to the doctors and they send you for a CT scan or a computer tomography scan, and if the Earth has a problem, we do a seismic scan, if you will, we do a seismic tomography. And I was talking to my colleagues in Uppsala, there is a few smart geophysicists, and they did this seismic tomography. And it's been a game changer because we find an anomaly down here. Below this level, the resolution gets down a little, but we find this anomaly here. Here we have different slices, and this anomaly sits at about. Oh, of course. Sorry, I forgot. So yeah, apologies. Let me go back actually one slide. I forgot the microphone. So here we were testing whether the lava chemistry is continuous. Schwarzenegger is in red here. The older eruptions from Fagradalsfjall are in blue, green, and yellow. And it seems that we have the same trend continuing. So the good news is from the chemistry, it looks like the same lava and therefore the same volcano. When we look at the mineral data, this is trace elements in olivine, there is good overlap and continuation. So we are pretty confident initially it was the same lava and therefore it implies one volcano rather than two. So when we want to find out what's going on inside a human body, we do a computer tomography. And when we want to find out what's going on inside the Earth, we do a seismic tomography. And I have some productive colleagues in Uppsala, geophysics colleagues, and they worked on this seismic tomography. And this has been really, really instructive because we have a larger anomaly here at about 9 to 12 kilometers depth. This resolution lower down breaks down a little, but the mantle is only really at about, well, 15 or deeper, and that means this reservoir sits in the crust. So it's not coming from the mantle, it comes from the crust, and there is earthquake swarms, that's the little dots here. They go up to Fagradalsfjall, and another set of earthquakes go up here to Schwarzenegger, and this is the inflation system that we see right now. The current eruptions are fed by this little reservoir, and this is what inflates and deflates and inflates and deflates, and that's causing the eruptions here, but it's also fed from this reservoir down here. The good news about seismic tomography is you can make a calculation of how much magma is in there. From the VP, VS ratios, you can calculate the amount of liquid and solid, and we did that. And there is a typo there. It's actually not 50,000 cubic kilometers. It should be 50 cubic kilometers. Apologies. I wanted to type it out in cubic meters first, but then the number got too long, and then I didn't correct it. Sorry. So my fault, but you get the idea. So we have 50 cubic kilometers of magma down there, and well, that's a good amount, but it's not huge. So the good news is there's not enough magma to flood Reykjavik. So, but will we have more eruptions? Yes, most likely. So this is the result of that, and we have one major system sitting in the crust, and this explains the initial crustal contamination in the isotopes, and now we're feeding new magma in. And how will this continue? Well, here's the more geochemical data from the Sundnúkar-Schwarzenegger area, now in red and pink. And we see some changes now. So the magnesium is going down now, the nickel is going down now, the chromium is going down now, the magma is becoming more evolved. And that means we're not seeing a lot of new magma, we see magma that's changing, likely in the crust. So again, that's actually good news. So, and here we also did more oxygen isotopes, and if the magma sits in the crust, it should assimilate more crust, and the values should change, and indeed we seem to have a mild trend towards lower oxygen, and this is typical for the crust in Iceland to have some lower oxygen values, and that means we now see magma that's been residing in the crust for some time, and it's not necessarily a new pulse of magma. So we're understanding the system better, but we will still have to face more eruptions. So, coming back to the model, this was the initial idea that we have a reservoir deep and we're feeding it all the way up from the mantle. And this is unfortunately no longer sustainable. This, I believe, is wrong. It's a very nice model, and I'm very sad to see it die, but we cannot sustain it anymore with the new data. This model wasn't bad. It was a good attempt for the time to explain it, but it's also not perfect. So we have to be a little skeptical about our early model as well. The reality is, I think it looks more like this. And here we have a complicated reservoir system, a plumbing system, likely with multiple pockets. This was my hypothesis. And actually, the reality is not so bad. I was quite chuffed how close we were. So here we have one major reservoir, maybe something deeper, but we cannot resolve this, and some smaller pockets high up, and they can feed this. So it's a complicated plumbing system, but it's a single plumbing system. So we published this later this year, and this got picked up by people in CNN. I suggest you read this paper, not that paper, because the media is always distorting it a little. But I think we have a good answer now for the dimensions of the magma system. So coming back to these three hypotheses, these was the models we started with, and it's this one here that I think is most realistic and that I suggest to be the working model for the upcoming eruptions. So I think there's reasons to stay positive despite the bad situation, because the magma system is not so big and Reykjavik is not directly in danger, neither is the airport. However, the Svartsengi power plant is in danger, and so is Grindavik town. So this cannot be changed right now. Let me sum up. What have we learned? Well, high-resolution temporal sampling of rift eruptions, they reveal considerable changes in La Palma as well as in Iceland. There's evidence for early crustal storage, and early eruptions are likely magmas that have been sitting in the crust for some time. So we need to be a bit careful or mindful. Sorry, there's a typo. We need to be a little careful with assigning everything to the mantle, because detailed work reveals that initial lava eruptions may not have come from the mantle. So although both La Palma and Iceland are plume-related, there is no anomalously low oxygen found when filtering the data carefully, and that means we can determine with significant certainty the oxygen isotope composition of the mantle in those areas. We have also learned that multi-reservoir magma supply systems are a bit messy, so the eruption products are complicated to read. And at present, it seems, however, that we have one plumbing system for both La Palma as well as for the Reykjans. For La Palma, we are expecting more eruptions, but the frequency is very low. Statistically, there's a 50% chance for another eruption in the next 50 years, but there we have a very high population density. Iceland will likely have more frequent eruptions, but the population density is much lower. But we have infrastructure, and infrastructure is always going to be a problem because we cannot move it. And the bitter lesson here is that rifts don't care what we put on top of it. So we need to be careful to assess the geology first before we build more power plants and things like that, because the real problem is that we put things there, not that the volcano erupts. The volcano was there all along, and humans have a slightly distorted perception of this. So it's our job to understand the volcano and be careful with it, rather than blaming the volcano for destroying the things we carelessly put in its way. So I'd like to close with this last video. Can I have a little click here? This is from spring last year. This is now Svartsengi lava. So, I say thank you for your attention, and I hope you found this useful.
Okay. Okay, thank you very much, Val, for your presentation.